In this video, we're going to talk through about how light slows down as it passes through a phase object, and we're going to calculate that phase difference that it experiences. And then we're going to talk a little bit about constructive and destructive interference. Both of these bits of theory are important to understand how phase contrast microscopes and DIC microscopes work. So we talked through in the last video about how a phase object, that is an object with the index of refraction larger than that of the media around it, causes light to slow down. You can see that here on the figure on the left. You can also see it on the right, perhaps a bit more clearly. So these are a series of wave fronts that are moving towards this specimen, or a cell in our case. As the light passes through it, it slows down. So you can see that once the light exits the specimen, it's basically shifted a little bit to the left relative to the light which is passed above or below the specimen. So we're going to quantify this difference. It's known as a phase shift a bit more rigorously. So this is after the light which is passed fully through the cell. We have the red light here, the red waveform here. It's been retarded relative to that of the light which passed the media only. And the distance, the amount that's been retarded is denoted by phi. And in this case, we're going to call it phi an angle. We're going to have units of radians. So to calculate that, we need to calculate something known as the optical path difference. Now the optical path is simply the distance which light travels times the index of refraction. And we're going to compare that for this path which moves through the cell of thickness t with light which moves to the media only. So the index of refraction of the cell is nc, and the index of refraction of the media surrounding the cell is nm. So the optical path difference in this case, we can write that down as simply the thickness of the cell times nc, that's the red path, minus the thickness of the cell times nm. Now we're going to ignore the bits above and below the cell and the media, since the optical path in both the red and blue cases in that region are the same. So we can factor out a t here. And this is the optical path difference now of these two different light paths, which gives you a measure of how long it takes light to pass through these two different regions, or along these two different paths, the red and the blue. But we want to write this in terms of an angle. So we need to consider the wavelength of the light which is passing through this object. So we're going to write down the phase difference. And again, this is going to be called phi. That's going to be simply 2 pi over lambda times OPD, so we have in the previous line. And this is the wavelength of the light we're considering. And this is in radians. So we see I have a 2 pi here. If this was a 360, this would be in terms of degrees. But if the OPD is equal to 1 complete wavelength, then the light passing through the cell will be delayed by an entire period. If OPD was half of a wavelength, so half that of lambda, then it would be delayed by a phase of pi, so it could be completely out of phase with the light which passed through the surrounding media. So this is in terms of an angle. So we want to quantify now what is the typical phase difference that's experienced by light as it passes through a cell. So we'll consider this case here. We have a typical cell. We'll consider it 5 microns thick, and it has a refractive index of 1.360, while the media surrounding the cell has an index of refraction of 1.335. And we're going to calculate the phase difference caused by this cell. So we're considering a typical cell here. The size, if you note, is somewhere in between that of a typical bacterial cell and a eukaryotic cell. And this is a typical index of refraction you might find for both the cell and the media. This gives us an idea about the kind of phase differences we'll be dealing with in imaging cells. So we'll plug this into an equation. So first off, we have to assume a wavelength. So if we use white light, it's composed, as you know, of many different wavelengths. So for this case, we're going to consider green light, which has a wavelength somewhere in the middle of the range, which composes white light. So we have lambda equals 540 nanometers, which is the typical value for green light. Okay, so then we'll just plug that into our optical path difference equation. So we have OPD is equal to 5 microns. Times 1.360 minus 1.335. And that leads to an optical path difference of 0.125 microns. Or it's the same as 125 nanometers. Okay, so then for our phase difference in terms of an angle, we'll take 2 pi divided by 540 nanometers, multiplied by 125 nanometers. If you do the math on that, that's going to be equal to 1.45 radians, or, it's more intuitive for you, 83 degrees. So this is about 1/4 of a wavelength. So it's been shifted. The light which is passing through the cell has been shifted relative to that of the light which is passing through the media around it by about 1/4 of a wavelength. So this gives you a typical idea about how much light gets slowed down relative to the light which passes around your sample.